Okay, here's problem number 6 from assignment number 8. A car is traveling on a straight road, and for 24 seconds, the velocity is given with that piecewise graph. Let A be the acceleration at time t in meters per second. For 0 to 24, right, the piecewise function that defines A of t. All right, so we got A of t is a piecewise function. All right, and by the way, those pieces are going to be from 0 to 4, from 4 to 16, and from 16 to 24. Are we all agreed there that the pieces of the velocity equation can help us find the acceleration? Now, what is acceleration's relationship to velocity? It's the derivative, and of course, derivative is just a fancy way of saying the slope. So I'll do the easy one first. Hey, from 4 to 16, the slope of that line is 0. Oh, there's 0 acceleration. There's no change in velocity. If you're moving at a constant velocity, you're not accelerating, you're not deaccelerating. All right? So what about this other part? Hey, I'm going from 0, 0 to 420. It seems to me that the slope of that line is a rise of 20 divided by a run of 4. I say that the acceleration there would be 5, and I suppose I should probably put in a unit. This would probably be meters per second squared. And then lastly, what's going on between 16 and 24? I see a rise of negative 20 while we're doing a run of 8. So negative 20 divided by 8. 5 halves? Okay, so 5 halves, negative 5 halves meters per second squared would be the acceleration during that thing. Oh, what about less than or equal to or greater than or equal to signs? Should I put some of those in? No! Trick question. Why not? Why isn't it not appropriate to say that an acceleration exists at that precise moment? Because the derivative of that function does not exist there, and acceleration is the derivative of velocity. So we purposely leave off the greater than or less than signs because the acceleration doesn't exist. And so there's our answer there. Are we okay?
Yes.
All right, because I'm going to have to erase this so we can do part B. And I don't know how well we'll do part B, but we'll try. Okay, so I erase the ink, and let me readjust the screen here. Oh, you can barely read that, can you? I'll get the graph on there and the question. Let's try that. All right, find the average rate of change of velocity on the interval from 8 to 20. Find the average rate of change. So the average rate of change in velocity, the average rate is going to be the value of the velocity at 20 minus the value of the velocity at 8 divided by 20 minus 8. So there's our average rate of change equation. The value of the velocity at 20, is that 10? It looks like, can we confirm that? Well, no, but we do know that the rate of change of that line was negative 5 halves. And when we go from 16 to 20, we moved 4 units. So 4 times 5 halves is negative 10. So we lost 10 units. So indeed, we went from 20 down to 10. So the velocity at 20 is definitely 10. What about the velocity velocity at 8. That looks like it's going to be a little bit easier. It's going to be 20. And then 20 minus 8 is 12. So it looks like it's negative 10 over 12 or negative 5 over 6. And that'll be meters per second squared. The unit on the top part of the numerator of that fraction is meters per second, and then on the bottom, those are differences of 2 times, that's in seconds. So it's meters per second squared. Does the mean value theorem guarantee a value C for C between 8 and 20 such that V prime of C is equal to the average rate of change? No. MVT does not apply. Why does the mean value theorem not apply? Go ahead, Joey.
There's no continuous derivative.
Okay. V is not differentiable on the interval from 8 to 20. Which is another way of saying is the derivative is not continuous on that interval. So it does not meet the conditions of the mean value theorem. And that should make sense. It's like, yeah, we already found out the acceleration on this was 0, the acceleration on this part was negative 5/2. Is there any place where it's equal to negative 5/6? No. But the mean value theorem says that's okay because it wasn't differentiable to begin with. All right, that's problem number 6.